Okay, good morning. So, if you remember, we had left this problem from the previous session, and then let us do that problem and then continue our lesson. Um, so here, do you have any ideas? So let us see what is the problem. Let A and B be commuting idempotent matrices. So you know that idempotent matrix A means A squared is equal to A, and we had a theorem about that. Am I speaking slowly or very loudly? Can you hear me well? Because there are some AirPods I cannot hear myself very well. Okay. So here, idempotent matrix means a matrix whose squared is equal to itself, and hopefully you know something about idempotent matrices. You'll know that not only the second power is equal to A, any power of that matrix would be equal to itself. Yes? Okay, so how should we solve this problem? And of course, this is extremely high power. So, do you have any idea what to do? Yes, Carl?
Maybe calculate a plus b minus ab squared.
Squared, yes. And so what is your strategy to start with that? So let me write. Your idea is correct. So you say that I will start with a plus b minus ab to power 2 instead of having that huge power. Okay. So what is your idea now?
Then, well, I calculated it and it became
How did you calculate? That's my point. Did you use any algebraic identity or you just simply multiplied them 2 times? Yeah, that's probably a good way to do that. Uh, but let me tell you, I want you to use this algebraic identity. But of course, this algebraic identity is among numbers. Do you remember? If I have a plus b plus c, I don't know how many of you remember last year we were doing this mathematics inspiration. We will learn a little bit about algebraic identities. So let us consider, I don't know how many of you remember, it is the first one to the 2, the second one to the 2, the third one to the 2, plus 2 times the first one times the second one, plus 2 times the first one times the third one, and finally plus 2 times the second one times the third one. So that is an algebraic identity that we have in algebra. But of course, this is among numbers. You shouldn't expect that this will work for matrices because matrices do not enjoy commutativity. Yes. Okay. But do you think I can use this algebraic identity here? At least we have something about commutativity of A and B. So if I want to use this for matrices, it is not only enough to have matrix A and B commute. We should also have matrix A and C commute. We should also have matrix B and C commute. Yes. So if I want to use this algebraic identity, if you don't want to use the algebraic identity the way that Carl presented is completely okay. You really don't need to do that, but I just want you to know about these things. That's it. So if I want to use this identity, I want to give the role of A to this A, I want to give the role of this B to this B, and I want to give the role of C to minus AB. But there is only one condition that I can use this, is that I should confirm that this is commuting with this one, which is directly given to in the problem, so I don't need to do anything. But I also have to confirm that this matrix and the last one commute. We should also confirm that the middle one and the last one commute. Okay, so these two are not trivial. Yes, we have to check them. So what does it mean? Let us check. So I am asking myself, is the matrix A commuting with the last matrix AB? If this is correct, I need to be able to convince myself of this. Do you agree? This is the meaning of matrix A and AB commute. If I can confirm that, it means that these two matrices are commuting. Agree? Okay, so I don't know what we can do. For example, I can start from the left-hand side. I would say the left-hand side is A times AB, but in the problem you are telling me that A and B commute. So instead of AB, I can write BA. but I know it is associative. Matrix multiplication is associative, so I can put the pair of brackets around the first pair. And then again, I use the commutativity of AB. I can write it as BA. Am I right? Or should I want to have AB. So it's already there, yes? Yeah, it's already there. It's much simpler than I thought. So you see, I was able to start from the left-hand side and using the commutativity of A and B and then associativity, I was able to reach the right-hand side, yes? So similarly, we can show that B times AB is equal to AB times B. Okay, so it means that now I am on the safe side. Now I can use the algebraic identity if I want to. So let us just do it together. So therefore, the algebraic identity can be used. Okay, and now I would say that A plus B minus AB squared is the first one to the 2, the second one to the 2, but be careful about the other one, plus the second one, the third one to the 2, so you have to write it in this way, and then you write 2 times the first one times the second one, minus 2 times the first one times the third one, and minus 2 times the middle one times the third one. Is that acceptable? Yes? Okay, now what we know, can I write this as a squared b squared? So this is the only formula that you need to be careful. In general, ab to the n is not equal to an bn unless you know that a and b are commuting. So here we know, so we can use the formula. So then it becomes it becomes a squared plus b squared, and then becomes a squared b squared, and then I have 2ab. I can use associativity. I can write a times a, b minus, for example, I can write minus 2b, and I change a and b. Okay, so let me just write everything and then I can substitute, yes? And then you know that this can also be written in this form. But you know that A and B are idempotent matrices. So we know that A squared is A. We know that B squared is B. Yes? So I can continue. Instead of A squared, I can write A. Instead of B squared, I can write B. And then the same story here. AB plus 2AB. Yes, minus 2AB minus 2BA. But let me simplify it again. A plus B. So AB plus 2AB becomes 3AB. Okay, so these two are gone actually. So I am left with AB. But instead of BA, I can write again AB. But then what happens? This becomes A plus B minus AB. So do you agree? So after this calculation, this was an interesting example. A plus B minus AB to the power of 2 becomes exactly equal to itself under these conditions and commutativity of A and B. So what can I conclude about the power 2021 power? Yes?
I wanted to say that you could conclude that a plus b minus ab is a.
Idempotent. Exactly. So therefore, A plus B minus AB is also an idempotent matrix. Okay, so therefore, any power of that, including this power given in this problem, is equal to itself. And of course, it is clear that we cannot simplify this more than that. So that's also, I would consider a good problem. It is simple, but you need to be a little bit clever to understand the rule. Yes?
This is a very useful type of question, so you can adapt it for any.
Yeah, exactly. So yeah, these kinds of questions. So because when you start working with matrices, you might think that many things are trivial, so there are nothing to think about. But yes, you have to think sometimes. Okay. Any questions here? Okay, so now let us go to today's lesson. This is also a very simple lesson. And there is another terminology that I want to define for you here, and that is called the transpose of a matrix. And that's a very simple idea. So if you have an m by n matrix, the transpose of A is denoted by this symbol. This is more standard. Some people, in some books I have seen, they put lowercase letter t, and some books even I have seen they put prime, just prime. But let us stick to this more standard convention. So the transpose of this matrix is denoted by this symbol, and it is defined to be an n by m matrix. So if you start with an m by n matrix, its transpose is n by m matrix, such that its ijth entry is the jith entry of A. So in principle, you are interchanging the role of rows and columns with each other. Yes? So that's it. If you have this matrix, you see this is a 2 by 3 matrix. This is the first row, and this is the second row. If you want to set up the transpose of that matrix, you will put this as the first column, and you will put this as the second column. So you see that this matrix is a 2 by 3 matrix. When you transpose it, it becomes 3 by 2. So that is called the transpose of that matrix, as simple as that. Is that clear? Okay, so this transpose, hopefully later when you go to university, you see that we don't have time to talk about these applications, but there are many applications with these definitions. Okay, so here, for any matrix A, I hope that this is clear for you. So if you remember, what is the meaning Ri of a matrix, any matrix, it means the ith row of that matrix, yes? So this tells you that the ith row of the transpose matrix is equal to the transpose of the ith column of A. So for example, if I ask you what is the first row, by the way, might be this is also a good example. If I give you this matrix 1, 2, 3, what is its transpose? Yes?
1, 2, 3, but written
in the column form, yes? 1, 2, 3. And of course, if I give you this, if I ask you what's the transpose, it becomes into the row form. Yes? It's clear. So now if I ask you, for example, what is the ith row of A transpose? Let us take I to be 2 to understand this. This is very simple. So the second row of A transpose is 2, 5. On the other hand, the second column of A is 2, 5. Yes? Now if I transpose the second column, it becomes exactly 2, 5 as demanded. Yes? So it is simple that the ith row of the transpose matrix is equal to the column, that column of A, but its transpose. And the same is true if you consider the columns instead of rows. Yeah, is that clear? But they are very simple actually. Let us do one example. Let A, B, and C be 4 by 5, 6 by 4, and 6 by 7 matrices respectively. Okay? So let me write here in front of your eyes. So A is a matrix 4 by 5. B is another matrix 6 by 4. And C is another matrix 6 by 7. We want to find the order of this product. Okay, so what is the order of this product? Yeah, it is very clear. What is the order of A transpose? It is 5 by 4, yes? And what is the order of B transpose? It is 4 by 6. what is the order of C itself? It is 6 by 7. So can you tell me what would be the final order?
5 by 7.
It would be 5 by 7. So it's very simple, yes? Is that clear for everyone? Now I would recommend you to start solving this problem, but of course, I don't know, I don't want you, so I have given you two matrices, and I have asked you to determine the entry of this matrix that lies on the third row and first column. Of course, you can set up all the matrices here and multiply all of them, but that's not my goal. I want you to remember the formulas and the methods that I described before for you, okay? So let me pause the video and wait for you a little bit. Okay, so we want to determine the entry of A transpose BA that lies on the third row and the first column. So what does it mean? It means that I am not interested in the entirety of this matrix. I am interested in only one of these entries, which lies on the third row, yes, and the first column. So I don't know, how do you interpret it? There are two ways to interpret this. Let me put A3 alone and then use associativity, put B and A together, okay? And then I'm looking this entry. So do you remember, how can I write that? I am interested, if you remember, if I have two matrices M and N, and if I am interested in ijth entry, I don't need to calculate everything. What I take the ith row of the matrix on the left, and I multiply it by the jth column of the matrix on the right. Yes? So let us just do that. So this becomes the third row of the matrix on the left, which is this, multiplied by the first column of the matrix on the right. But we just learned, what can I write instead of this one? Do you remember? I can write the third column of A totally transpose. And then if I ask you, how can I calculate the first column of a matrix, the jth column of a product, do you remember what was it? The jth column of a product? So you need to take the matrix M, total matrix M, but just multiply it by the jth column of matrix N. So that was a rule, okay? So here I will do the same thing. So I will take the whole matrix B, but I just multiply it by the first column of A. Of course, you might say that you are spending time on writing these things, but I think from a theoretical point of view, it's better to understand what's going on. And I think now we can do everything we want. Yes, so let us substitute. Be patient. I don't want to be quick. So the third column of A. What is the third column of A? This is this matrix. So it becomes 3 minus 1 and 2, and then I have a transpose on top of that. And then I have to write the matrix B in its entirety, 1, 1, 0, minus 1, 1, and 2, 1, 1, and 4. And then I multiply it by the first column of A again. First column of A is 1, 0, 4. But you see, on the left-hand side, I have a transpose of this column matrix. So what does it mean? It means that I can write it as 3 minus 1, 2. Okay, multiplied by 1, 1, 0, minus 1, 1, 2, 1, 1, 4. The reason that I am solving it in this way, because this way of thinking about matrices is theoretically important. I'm not saying that I'm saving so much time. So here you can decide. There are three matrices being multiplied. You can decide to do this one first, or this one first. It doesn't matter. I always prefer to do this one first. So let me just write 3 minus 1, 2, and then I multiply this by that. So the first row will be multiplied by the first column. It becomes 1, 0, and 0, so it becomes 1. The next one becomes 7. The next one becomes what? 17. Am I right? And then if I multiply this, it becomes 3 minus 7 plus 34. So I didn't get that answer, Carl.
Yeah, I made a mistake.
So could you confirm now that my answer is correct? So it is 30 if I am right. No one so got that? So let me double check my answer. So I multiplied this by that, it becomes 1, 0, 0, so it becomes 1, that's correct. I multiply this by that, it becomes minus 1, 0, and 8, so it becomes 7, that's also correct. I multiply this by that, it becomes 1, 0, and 16. If I add them, it becomes 17, and that's also correct. Then 3 times 1, minus 1 times 7, 2 times 17. So everything seems fine, and the answer is 30. Yes? Is that clear? Okay. Now let us go here. What do you think? Do you want to think about this problem as well? So let me read it for you. Hopefully there is no, because I don't see any 2 here. Let us trust the way that I typed it. So let A, B, and C be real numbers such that we know that A squared plus B squared is greater than C. And then X is this column matrix and A is this square matrix. Show that the equation equals to 0, this combination equals to 0, represents a circle. Determine the center and the radius of this circle. Okay, so I would say that this part you shouldn't have any problems with. So if you don't mind, let me pause the video again and give you the chance to think about it, okay? And then we can discuss together. Okay, the first thing comes to mind is to calculate, because we don't know circles in the matrix form. So here, first of all, tell me, is it so do you think this is a typo? Because usually I denote matrices with a different symbol. But do you think this is number 0 or matrix 0 before starting the calculation? Yes? No, it matters. Because when you if I ask you to write an equation for a circle, you don't involve matrices. So if this is the 0 matrix, so what's the order of that matrix then? But this is definitely a number. Why? Because x is 3, sorry, x is 3 by 1, yes? So x transpose becomes 1 by 3. A is middle one, is 3 by 3. X is 3 by 1. Yes? So if I ask you what is the product at the end, it becomes a 1 by 1 matrix. So it definitely is a number, not a matrix. Yes? Okay, so this way of thinking is also very useful, especially if the problem is hard. So what I do, I would just put them inside. So x, y, 1 transpose. Instead of A, I put 1, 0, A, 0, 1, B, A, B, and C. And then I multiply it by x, which is x, y, and 1, and I equate it to number 0. But then we know that the left-hand side, this transpose of that column matrix is simply this row matrix. And then I would repeat everything else. Yes? X, y equals to 0, but then I start multiplying the second pair. I usually start multiplying the second pair first, so it becomes how much? It becomes, what should I do? I need to take this row and multiply it by this column. I multiply 1 by x, 0 by y, a by 1, and add them together. So it becomes x plus a. Yes, agree? And the second one, it becomes y plus b. And the last one becomes ax plus by plus c equals to 0. Do you agree? Yes? And now what I do the matrix multiplication once more, so I have to take this one and multiply it by this column. So what I do, I take the first one multiplied by the first one. I multiply the second one by the second one. And I will multiply the last one by the last one. And of course, I have to add them together. In principle, you should have a matrix sign around that, but because this is just simply a number, you identify it with the number itself, and that you don't need to put the matrix sign. Now, if I expand that, x times x is x squared, so this x times x is x squared, y times y is y squared, And then what I have here, I have a times x from here, another ax from here, so it becomes 2ax. Yes, and the other one for the same reason becomes 2by, and the other one is c equals to 0. So that is the first part of the problem. So you were able to actually understand what is the equation. Now you want to convince yourself that this is actually a circle. So if you don't mind, let me move it a little bit lower here. So, okay, how should I convince myself that this is an equation for the circle? And if that's the case, okay, here is also determine its center and its radius. You had the equation of a circle before, yes?
It's just one.
No? So how do you come to that conclusion?
Because I was thinking maybe the x is like, maybe this is a famous matrix where x is the...
No, it's not a famous matrix, but it is a famous equation. So if you remember, I was teaching you this in Matrices. So what is an equation of a circle? Do you remember? So even if you don't remember, you should be able to understand it on your own. So for example, assume that I have this coordinate system and I have a circle here. And let us assume that its center is alpha and beta. And let us assume that its radius is r. Yes? Yes? Do you want to say something?
Yeah, we use the distance formula.
Yeah, that's the distance formula, yes? Because if I have a point on this circle, so let us call it M, with coordinates x and y, we know that the distance from the point M, it doesn't matter which point, all the points enjoy the same property. The distance from M to the center is always equal to the radius. And I don't know, if you don't remember the distance formula, that's another big trouble, okay? So you need to remember these things. If you don't remember that, you have to find it yourself again. So that's what I'm saying, that if you don't have enough important tools in your memory, then you will be in trouble. But anyway, let me just ignore that part. The distance formula is the difference between x coordinates to power 2, the difference between y coordinates to power 2, and a square root. Yes? And this should be equal to the distance, which is the radius. And then you raise it to power 2, it becomes x minus alpha squared plus y minus beta squared is r squared. And this is what you see in the books. This is the standard form of an equation for the circle whose radius is r and its center is alpha and beta. Is that understandable? So this is the way that you need to think it. But of course, this is still a little bit far away from this standard way. In the standard way, I have two complete squares. So this motivates you how to act. You have to make up two complete squares, yes? And this is not very hard. For example, what can I do? I can write x squared. I put 2x next to it. Let me put an empty space here. And I do the same thing for y. I write y squared plus 2by. And I put an empty space here. Okay, and then what is left for me is a c equals to. So tell me, what do I need to put here to make it a complete square? Yes? I need a. No, not a squared. Yes, I need a squared. So I put a squared here, but I cannot just put an a squared here unless I compensate for that by putting a squared here on the right hand side as well. Okay, and the same story here. I put b squared here. To compensate for that, I put a b squared here as well. And now if you see, I can collect the first terms. It becomes x plus a squared. And the other one is y plus b squared. And then on the right hand side, I have a squared plus b squared. And then I move c to the right. Yes? Now you realize why this condition is actually given to you. A squared plus b squared is supposed to be greater than c, because if this is not the case, this becomes negative. And if this becomes negative, you have a contradiction, because on the left hand side, this is non-negative. This is non-negative, so the whole expression is non-negative on the left, but it would be negative on the right, which is not possible. So that is the reason that they have mentioned that a squared plus b squared has to be greater than c. Okay, and then hopefully you agree with me that I can write it in this form, reform it. I can write minus a squared, because I want to write it as completely a standard form. minus b to the power of 2, and do you agree that I can write square root of a squared plus b squared minus c to power 2? The reason that I put this in this form because I want to compare it with the standard circle equation, x minus alpha y minus beta squared r squared. So yes, this is the standard form, as we discussed about that right now. This is the standard form of the equation of a circle. Okay, so now can you tell me what is the center of this circle? Yes, just say it. Yeah, center is minus a minus b, and what is the radius? Yeah, a square root of a squared plus b squared minus c. Yes, so it means that you can write an equation of a circle in matrix 4. Yes. Okay, so let us also talk about this theorem, which is extremely important. So the properties of the transpose. Okay, so they are extremely important in matrix algebra. So I think some of them are trivial, we can skip them. So for example, I think you could also guess yourself that the transpose of a transpose becomes the matrix itself, so you are doing the same operation 2 times. Yes, is that understandable? Okay, but this one, is it also clear? If I multiply a number into a matrix, it becomes a new matrix. If I want to take the transpose, I can take the transpose first and then multiply it by a number. It doesn't matter, yes? Because when you multiply this number, it goes into all the entries, and when you interchange the rows and the columns, you are taking R with you, yes? So that's clear. And that's also clear if two matrices are the same, their transpose are the same, and if the transpose are the same, the matrices are the same as well. Okay? But this one, I prove this one, and especially the very important one, the last one. Okay? The proof of this one is also not very strange. So, for example, I would say, let me write the proof here. So number 4, for example, I would say that for definiteness of discussion, so let A and B be, for example, m by n matrices. Okay, so if A and B are m by n, so A plus B is also m by n. When I transpose it, it becomes n by m. So the left-hand side is an n by m matrix. On the other hand, A transpose is n by m, B transpose is n by m. When I add them, it becomes n by m. So from order point of view, the order of the matrix on the left is equal to the order of the matrix on the right. But we need to consider the entries. Okay, so how should I consider the entries? I would say that A plus B transpose. For example, let us consider the ijth entry. So what can I write? According to the definition, I can write the jth entry of this matrix, yes? But then according to the definition of addition, you can write the jth entry of A plus the jth entry of B, and then of course you can write A transpose ijth entry, and then you can write B transpose ijth entry, and then you can write A transpose plus B transpose ijth entry. So it means that ijth entry of this combination matches with the ijth entry of this combination. And here I and j are arbitrary indices, so it means that this is in total true. Yes? But of course, intuitively, it's also clear, yes? But this one is a little bit more technical, and I want you to pay attention to it. So if you want to take the transpose of a product, you are allowed to take the transpose of each one of them individually, but it is completely crucial to remember that you need to write the second one first and the first one second. So it's very important to interchange these positions. So let us do that. How we can prove this one? Again, you need to convince yourself that the orders are the same. But of course, here I have written operations are defined. So if this operation is going to be defined, let me be more careful here. So I would say let us consider that A is an m by n matrix because AB is supposed to be defined. If this is not defined, of course, this doesn't make sense. To make AB defined, I need to have B, for example, n by P. Okay? Now, the order of the left-hand side, what is the order of the left-hand side? If I multiply them, the order becomes m by p. When I transpose it, the order becomes p by m. So if you ask me what is the order of the left-hand side, I will tell you p by m. But if I ask you what is the order of B transpose, it is P by N. And if you ask me what is the order of A transpose, it is N by M. And if I multiply them, clearly it becomes P by M, which is exactly the same thing. So from order point of view, they are exactly the same. Okay, so what is important to check is to check the entries are the same. So you need to think a little bit about that. So I would write AB transpose. I concentrate on ijth entry of this combination. What can I write in front? Can you tell me what would be the first step? What is the ijth entry of AB transpose? Yes? No? ABJI, yes, yes. You mean ABJIth entry, yes? That's what you mean. Yeah, that's correct. That's the definition of transpose, yes? But what can I write in front? Can you tell me? How do you think that I will continue to prove this theorem? Yes?
We use the definition for
Which contains a
multiplication, which contains a
sigma. Yes, that's a multiplication. That's a multiplication AB, and you are interested in the jith entry. So what you do, if you remember, I write it and you fill it up for me. There is a sigma. I need to put a counter for my sigma. It starts from 1, but can you tell me up to where? Up to, no. So I will make the exam extremely hard, okay? I told you up to the number of columns or rows, this common number, yes? So we go up to n. Okay, again, I have a little a and little b. Can you tell me what is the index, what is the starting index of a? Yes? It's j, yes. It starts, a starts with the first index that you see here. B ends with this index that you see here. But what is the index for what are the other indices for A and B? Yes? What? No. So what's the role of K? Yeah, it should be K, yes? So it becomes AJK and BKI. Is that understandable? So that's the way that we write it. Okay. But what can I do here? Do you agree if I write something like this? I can write sigma. So you see that here, this is now connected to A and B themselves, but I want to, so if you don't mind, let me write it everything like this. So it becomes A, it's easier probably. Matrix A, J kth entry, matrix B, K ith entry. So what can I do now? K goes from 1 to n. If I insist to write A transpose here, what should I write for indices now? Because I have to somehow connect it to A transpose and B transpose. I started from a transpose, but there is no track of transpose left in this argument. I need to somehow go back to the transpose matrix. So I have somehow to write A transpose, but what should I do? Yes? It should be KJ, yes? And then for the other one, I can write B transpose JK. But do you think this is the standard definition of matrix product? Yes? What? What?
on the
Yes. Okay. Sorry. Thank you. Yes. So I have to write IK. This is what you mean. Thank you. Okay, but do you think this is now the standard product of matrices? If we swap them. Exactly. So that's what I wanted you to feel, yes? Because you see, the standard matrix multiplication have the middle indices the same. But here now the middle indices are not the same unless we realize we have to swap them. And then this is the reason that you get this swap there. Yes? So then what happens, it becomes the sigma, k goes from 1 to n, B transpose IK, and then A transpose KJ. But I hope that you can read the other way around. Can you tell me what is this one? This is the entry, some entry of the product. But what is the product? B transpose, A transpose. Can you tell me what is the entry? What's the entry? It's IJ. Yes? And now look, if you compare the first one and the last one, you immediately realize the ijth entry of this matrix is exactly equal to the ijth entry of this matrix. So you that was the important thing. You feel it yourself that you have to swap them, yes, so that make them as the standard definition. So these are extremely important properties of transpose matrix, of the transpose matrix. Okay. Um, so let me see. Might be there are some things that I want to talk about before going to this. Something that I want to mention. What do you think? If I have a to the power of 2 and then transpose, do you think I can write a transpose a to the power of 2? Assume that A is a square matrix. Here I am squaring, then transposing. Here I am transposing first and then squaring. Do you think that they are equal there, or you can bring a counterexample that they are not? So is raising to power operation and transposing operation are commutative? This is the meaning of commuting these two operations, yes?
I think they should be.
Can you elaborate on it more?
When we when we square the matrix A, we multiply the
Yeah, it's very hard to imagine it in that way. Do you agree? Because matrix multiplication is fairly complicated. Might be we are not able to keep track of all these details. So you need to convince me so that you yourself is also convinced. Huh? Yes? No, it's much simpler than that. It's in front of your eyes. No, of course it is not complete. Yes, if it is in the idempotent, yes, but it is probably not. But it is in front of your eyes. Yes, Carl?
number 6.
Number 6, yes. So A squared transpose is what is A times A transpose. Yes? But this means I have to do it from the right to the left. But here both of them are the same. So it becomes A transpose. This A that you see here is the second A, but who cares, yes? Then A transpose. Now if I ask you what you see the same matrix multiplied by itself 2 times. So this becomes A transpose to power 2. So it means that you can interchange the role of transpose and powers. Yes? And by the way, there is nothing special about two matrices. So you can expand this A1 times A2 times up to AN and then transpose. You can use mathematical induction. If this product is defined in the first place, you can do it from the other way around. So A to AN transpose AN minus 1 transpose until you reach to A transpose A1 transpose. So this, if you want to prove it's mathematical induction, that's very easy. So that's, you can extend. You can also extend here for more than two matrices, again using mathematical induction. Yes? So in principle, it's an extremely, I don't know why I have forgotten to write that, but that's an extremely property. So let me write it with a different color. So if I raise a to some power n first and then transpose, it doesn't matter if I first transpose and then raise it to power n. Here, I would say both of them are of the same difficulty. It doesn't matter that much. If you first raise it to power n, you have to go through this hard work to raise it to power n and then transpose. The right-hand side is not easier. Of course, you transpose it first, but at the end, you have to multiply it n times. But it is extremely important to understand that when you can commute the operations, sometimes, of course, both of them might be the same, but one of them can be calculated for us much easier. This is not one of them, that it makes the life easier for us, but you need to know that, yes?
Is there a proof that if A is idempotent and we take the transpose of A, it will still be idempotent?
We can check that. That's a good question.
Then there is a case where that equation would.
So what you are saying, so let me for example, you are saying that I will write here and then I will clean that, okay? So I haven't put that enough space here. So you are saying that a squared is a, this is what you say, and now you are asking this question, do you think that the transpose is also idempotent? So it means that, do you think that this is true or not? This is your question. Okay, so let us check that. What is your answer? Is it yes or no? It's very simple now.
Yes.
It's a yes. Can you elaborate?
It's again the same.
So, for example, I want to show this question mark. I start from the left-hand side of the question mark. I would say A transpose to the power of 2. Okay, we learned right now. I can interchange the role of these two. So 2 goes down, T comes out, yes? But what is A squared? Because of your assumption, it is A. So instead of A squared, I put A, and then I have a transpose out of it. So yes, the answer is right. If a matrix is idempotent, its transpose remains idempotent. And it was very simple. So at least this is a very good example, by the way, for the application of this formula. Yes? I told you that this formula does not make life easier for you, but it values from theoretical point of view. So you were able to answer this question using that formula. Yes? Okay. So let me also continue. Yeah, there are two definitions. One of them is called symmetric matrix, a symmetric matrix, and a skew-symmetric matrix. Okay, if you have a square matrix A, sometimes it happens that its transpose is equal to itself. Okay, if the transpose of a square matrix, of course you know that it has to be a square, yes? Otherwise the transpose of a rectangle matrix doesn't match with the order. So from the order point of view. So it means that if you have a matrix A, sometimes it is possible to have this relation, that when you transpose it, it becomes again the matrix itself, then it is called symmetric. And then we say sometimes it might be skew symmetric. It means that when you transpose it, it is not equal to itself, it becomes negative itself. That's called skew symmetric. Okay, so these are the different types of matrices that are important in different contexts. So this matrix is a symmetric matrix, yes? If I ask you what is A transpose, what you do, you will put this as the first column, so it becomes 1, 2, minus 5. You will put this one as the second column, it becomes 2, 3, and 4. And you will put this as the third column, it becomes minus 5, 4. What was that? I don't see. Do you remember what is that? 7, yes. Okay, and now if you check, you see the same matrix. This is exactly the same matrix, nothing changes. So that's a symmetric matrix. And when we say symmetric, with respect to main diagonal, it is symmetric. Yes? So it means that this entry matches with this one, this entry matches with that one, this entry matches with this one. So symmetric, when you say symmetric, it means with respect to the main diagonal. Okay, but this one is not symmetric, it is skew symmetric. Why? So let me write it here for you. Let me change my color and write A transpose here. So what is A transpose? The first row should be written as the first column. And the second row should be written as the second column. And the third row should be written as the third column. Okay, now if I factor a negative sign out, it becomes 0, 2, minus 4, minus 2, 0, minus 5, 4, 5, and 0. And now if I ask you what is this matrix, you immediately confirm that that's A. And I have a negative sign behind that, so that's a skew symmetry. Can you say something before seeing the next remark? Can you say something about the elements on the main diagonal of a skew matrix? So you see that all of them are 0 here. Do you think that's a coincidence or this is a have-to? So I'm asking you, if I have a skew symmetric matrix, is it necessarily the case that all the entries on the main diagonal have to be equal to 0? Yes? If you say no, you need to provide a counterexample for me. So you need to give me a skew symmetric matrix which doesn't have that property. Okay, but you need to cook up the whole matrix. So if you want to say no, so you need to provide a real counterexample, yes? Okay, now read the remark. So they are always equal to 0, but can you cook up an argument why this is the case? Yes?
If you multiply the
Now let me ask you this question. If you have a square matrix, when you transpose, you start moving entries around except particular entries. What are those entries?
ones on
Main diagonal. They are not moved. Yes? When you do this transpose, every entry will move except those entries on the main diagonal. On the one hand, they are not moved, but on the other hand, because they are skew symmetric, they should be multiplied by a negative sign. So it means that I want a negative number which is equal to itself, because on the one hand it is not moved, on the other hand it is negative of itself. So it means that that number should be 0. So you can continue this argument for each one of those entries. So that is the case. So whenever you see that you have a matrix, at least one of them is not 0, you don't need to check. Immediately you can conclude that that's not a skew symmetric matrix. Okay, but of course, if all the entries are 0, still there is no guarantee that that's a skew symmetric matrix. You have to really check that. Is that clear? Okay, so let us do these two examples. Yeah, let me just do one of them and then we'll leave the next one for the exercise for the next time. So here you see uh, I have A, B square matrices of the same order. I don't know what about A. I don't know what is A and what is B. Are they symmetric or not? But I don't care. Whenever you construct this combination, it turns out to be a symmetric matrix. Okay, so you can start from any matrix that you like, even if it is not symmetric. But when you construct this combination, it's definitely symmetric. And the same is true here. Okay, so let me just do this and then we are done. So I want to show, can you tell me what to do? I want to show this combination is a symmetric matrix. What should I do? I need to follow up this definition, yes? I want to show that a matrix is symmetric. What I need to do, so I would say we have to show that A plus A transpose plus A transpose transpose is equal to itself. Do you agree? I want to show that this combination, regardless of the nature of matrix A, is symmetric. So it means that if I take the transpose of that combination, it becomes equal to itself. That's the meaning of being symmetric, yes? Okay, so let me just do that. According to the rules, I have the sum of three matrices and I want to transpose. So I would say the left-hand side, according to the theorem, it becomes the first matrix transpose, the second matrix transpose, and the third matrix transpose added. Yes? Are you happy with this? Okay. Now, the first thing that I don't know what to do with the first one, but I know something about the second bit. Transpose becomes equal to itself, yes? So this becomes A itself. And then I have a product and I want to transpose it. I can do it individually, but I have to write from the end to the first, yes? So what should I write? I should write A transpose, and then A transpose. Yes? Is that understandable, what I'm writing? Okay, but is there any difference for A transpose plus A and the other way around? No. So in principle, I can write A plus A transpose. But if I ask you what is this one, you will tell me again A, so it becomes A transpose. So we are done. I transposed this matrix and it happened to be equal to itself. So it means that we don't care about if A is symmetric or not, but if you take any square matrix that you like, you calculate this combination, at the end you will get a square matrix. So you can, for example, convince yourself by taking, I don't know, 1, 2, 3, 4. Definitely this is not symmetric, but you can calculate this combination. You will see at the end you will get a symmetric matrix. Okay, so there is a second part to this example, and there is example 8. I will upload this video and you will get access to these below the video. I would recommend you to work on these problems, okay? Yes, so I think next time we also talk a little bit about the trace of a matrix in more details, and then we stop there and then try to solve some problems on mechanics together. Any questions? Okay, thank you.